Particle accelerators are one of the great instruments used as much for scientific knowledge or industrial progress as for human well-being. Over the past 90 years, 24,000 accelerators have been built. 200 are currently being used for research purposes, such as the world's largest accelerator at CERN, the European Research Center in Geneva, Switzerland. Over the 27 kilometers of the accelerator's circumference, millions of particle collisions are produced every second. The resulting particle jets are analyzed by giant detectors, as here with the Atlas detector. The multiple detection systems installed in successive layers measure the charge, momentum, and mass of all the particles resulting from the collisions. This is how the Higgs boson was detected, confirming an explanation of the origin of the mass of all the particles that surround us and of which we are made. This discovery was rewarded with a Nobel Prize in Physics. This research on the ultimate building blocks of matter can potentially provide us with answers to some great puzzles of the universe, such as the nature of dark matter or the extreme scarcity of antimatter. At the facility called Soleil, located south of Paris, accelerators are used for a completely different purpose: to produce an extremely directional and bright radiation called synchrotron radiation, which can be used to probe the microscopic structure of all kinds of materials. Synchrotron light is produced each time the path of the particle beam goes through a bend. The electrical, magnetic, and radio frequency equipment extends over several hundred meters. The whole setup is aligned with a precision of 1/100th of a millimeter, and its temperature is stabilized to 1/10th of a Celsius degree. Dozens of beamlines serve the many experimental stations where inanimate materials such as silicon or concrete are studied, but also biological samples such as bacteria or cells. This synchrotron light is 10,000 times brighter than the sun. Illuminating a material with this beam allows us to probe its internal structure with a resolution better than 1,000th of a millimeter. These characteristics cover our needs in many fields in physics, chemistry, or material sciences. They also serve biology, pharmacology, environmental sciences, and even disciplines that study our cultural heritage. Here is a yeast ribosome, probed down to the smallest detail with the synchrotron radiation produced by the Soleil facility. The ribosome is like a factory within a cell that produces proteins from the genetic information borne by messenger ribonucleic acids. The function of this ultra-complex but perfectly coordinated assembly is to regulate cell growth. Many pharmaceutical studies have targeted the internal part of ribosomes: anti-cancer drugs to inhibit the development of cancer cells, or antibiotics to inhibit the synthesis of pathogen bacteria. Some accelerators are used exclusively for medical purposes, such as this one dedicated to cancer treatment in the Proton Therapy Center of the Curie Institute in Orsay. The issue is to eradicate the diseased cells while affecting as little as possible the healthy organs located in front, behind, or next to them. With proton therapy, radiation oncologists can use a particle beam with ultra-precise ballistic characteristics, which is highly useful for treating tumors neighboring sensitive organs, particularly in children. An accelerator produces beams of electrical particles that are used to irradiate and destroy cancerous tumors. When these particles are composite ions, also called hadrons, This method of treatment is called hadron therapy. When the particles are plain protons, like here, we speak of proton therapy. The energy, size, and direction of the particle beams produced by proton accelerators can be tuned to very precise values. This is why they can be used to destroy cancerous tumors deep within the body while reducing damage to adjacent healthy cells. This characteristic makes them a valuable alternative to conventional X-ray radiotherapy. Today, there are more than 100 facilities of oncology therapy throughout the world. 300,000 patients have been treated in this way so far. Accelerators are also used to produce X-rays or radioisotopes used in nuclear medicine. A total of 11,000 accelerators worldwide are fully dedicated to medical purposes. Accelerators are a very fantastic contribution to human society. But did you know that the motion of particles in an accelerator are fantastic as such? We can witness these motions thanks to the numerical simulations performed by the IFMIF collaboration between Europe and Japan. At the exit of the source of an accelerator, the beam of electric particles, here positively charged ions, is only a few millimeters in diameter. The strong repulsive force between charges of the same sign literally shatter the beam. You have to strongly focalize the beam using an axial magnetic field so that it can enter a long radio frequency quadrupole cavity. The beam, which is originally continuous, is grouped into packets so that the first acceleration boosts can be applied. A few % of particles are lost. The energy of the beam is still weak compared to the energy of the repulsive forces between particles. We must constantly refocalize the beam after each brief acceleration, hence this frantic succession of acceleration and focalization. After getting focalized by a number of electromagnets, the beam enters a cryogenic structure cooled to -270 Celsius degrees. The cryogenic device successively accelerates and focalizes the beam. The beam has acquired a power of several hundred kilowatts. The extreme heat of the beam coexists with the extreme cold of the cryogenic equipment, separated by only a few millimeters. From 1 billion accelerated particles, we cannot afford to lose more than one. The colors show the relative energies of the particles. The redder the particle, the faster it travels compared to its companion. After a number of refocalizations and defocalizations, the beam is sent to uniformly irradiate a target. But this three-dimensional movie is not enough to fully appreciate the motion of accelerated particles. We must add the three directions of movement, which are symbolized by arrows. This is when we enter a fantastic world of 6 dimensions. Let us take a closer look at the particle bucket. When passing through a quadrupole electromagnet, we can clearly see the focalization in one plane and a simultaneous defocalization in the perpendicular plane. Hence this transverse oscillation movement relative to the center of the bundle. A judicious combination of quadrupoles ensures a fully effective focalization of the beam. When passing through a solenoid that produces an axial magnetic field, the beam twists around the field. The stronger the magnetic field, the closer the beam twists around the axis. Here we see a frontal view of the beam. Between two such focalization procedures, an acceleration is applied, which we can see clearly only when looking at the beam from the side. So let us move to the side of the beam. The acceleration is caused by a resonant electromagnetic cavity. The electric component of the field accelerates the particles, but we have to make sure to apply less acceleration to those that travel faster and more acceleration to those which travel slower. This is why we see a back and forth oscillation around the center of the particle cluster, interspersed with a winding movement around the magnetic field mentioned earlier. After a number of refocalizations and defocalizations, the beam is sent to uniformly irradiate a target. Some very small particles that bring great good to human society.